Hi everyone. In this third video on section 6.1, we're going to go through two example problems. So let's do example problem number 1. A 2 kilogram pendulum has a system energy of 9 joules. What is the kinetic energy of the pendulum when the pendulum bob has swung zero point 0.1 meters above its lowest point? Okay, so I know that for a pendulum, the energy, right, the total energy, we'll write that in there. The total energy of our pendulum bob is always going to be the combination of kinetic energy and gravitational potential energy of the pendulum bob. Now, they do tell us that this pendulum has a system energy of 9 joules. So I do know what this total energy is going to be. It is going to be 9 joules. And we want to know what the kinetic energy is. This is great, right? I can just keep K as my unknown. Now, the other things I know is that we are interested in the moment in time when our pendulum bob is 0 0.1 meters above its lowest point, right? So I'm interested in how much kinetic energy do I have when I'm right there. So I could try to perhaps calculate how much gravitational energy I have at that particular moment in time. And that should allow me to then calculate how much kinetic energy I have. So I'm going to do a little bit of mg delta y in order to do this. So let's see, 9 joules is equal to my kinetic energy plus my mass, which is 2 kilograms, times g, which is 9.8 meters per second squared. And my delta y is 0.1 meters above my lowest point. So when I multiply all of that together, I end up getting 1.96 joules. So by taking 9 joules of energy in my system, subtracting the 1.96 joules of gravitational energy, I am now left with how much kinetic energy I have at that moment in time. And it should be 7.04 joules of kinetic energy. Great. Let's go to example problem number 2. A horizontal mass spring system consists of a spring with spring constant 50 newtons per meter and mass of 3 kilograms. The spring is stretched 0.2 meters and allowed to oscillate. How fast is the mass moving when it is 0.15 meters away from its equilibrium position? Okay, let's do a quick drawing here. So I have, my horizontal mass spring system. I have my equilibrium position. We'll just say it's right about there. I originally stretched, how far away from equilibrium? I originally stretched 0.2 meters away from equilibrium. How fast is the mass moving when it is 0.15 meters away from equilibrium? So 0.15 meters. We know that this is 0, but how fast am I moving right there? Definitely going to be something greater than 0, right? Because we know that, as we get closer and closer to our equilibrium, we have maxed out our velocity. So we must be speeding up between this location and this location. So what am I going to do? Well, perhaps I can use my knowledge that the total energy in this mass spring system is going to consist of kinetic energy and spring potential energy. Now, in the previous problem, we knew what that total energy was. The problem told us it was 9 joules, and they do not tell us this in this problem. However, we do know that at this extreme, where our spring is stretched that maximum 0.2 meters, we do know that at that location, our energy completely just consists of potential energy, right? Because at that position, we are not moving, thus our kinetic energy is zero. So what I'm going to do is I'm going to first, this is going to be my step one. I am first going to look at my extreme where my kinetic energy is zero. And I am going to use the spring energy equation, 1/2 kx squared, to try to figure out what is that total energy in my system. Now, the spring constant is listed in the problem. It is 50 newtons per meter. And this extreme is at 0.2 meters away from the equilibrium position. So when I throw this in my calculator, I find that the total energy in my system is 1 joule. Now, I can take that knowledge that this total energy is 1 joule, and I can now start applying it to this second location, this location where I actually want to answer a question. So my energy is still going to consist of kinetic and spring potential energy. The equation for kinetic energy is 1/2 mv squared. The equation for spring potential energy is 1/2 kx squared. Let's see if I can fill in all of my numbers and solve for my V. The mass is 3 kilograms. Let's put that in for V, or sorry, for mass. I don't know V, so I'm just going to keep that the way it is. Again, my spring constant is 50 newtons per meter. And now I'm at this other stretch length. So my stretch is now going to be 0.15 meters. And when I look at this, this looks pretty good because I'm still going to have 1 on the left-hand side of the equals. 1/2 times 3 is 1.5. So my first term is 1.5 v squared. And then 1/2 times 50 times 0.15 squared is 0.5625. So the only thing I do not know is the thing I'm looking for. So let's finish this problem by just doing the algebra. Let's get at V all by itself. So we'll start by doing 1 minus 0.5625, and we end up getting 0.4375 is equal to 1.5 V squared. So if we divide everything by 1.5, then we end up getting 0.2916 is equal to V squared. And so a quick square root will tell us that at that location, we are going to be moving at 0.54 meters per second. Beautiful.